In this video, we will discuss a greedy solution to the activity selection problem. So here is the problem. We are given a set of activities A1, A2 and so on up to AN. Each activity has a well-defined start time SI and a finish time FI. Two activities AI and AJ are said to be compatible if they do not overlap in time. For instance, let's assume the time increases from left to right. Let's say we have two activities A1 and A2 such that A1 starts here and finishes here. So this is A1, and let's say A2 starts here and finishes here. Now because these two activities have no overlap in time, they are compatible with each other. As opposed to this, if we have another set of activities, let's say A3 that starts here and finishes here, and A4 which starts here and finishes here. Now these two activities have some overlap in time, and therefore these two activities are not compatible. So our goal in this problem is to select a subset O of the input set S such that all the activities in O are mutually compatible. That is, none of the activities that are selected in O should be overlapping, and at the same time we want to maximize the size of this activity set O. Let's take an example to make this clearer. Let's assume we have these 5 activities A1 to A5 in our input set. Here are some possible output sets with compatible activities. Note that A1 and A3 do not overlap with each other and therefore they are compatible. Similarly, A2 and A4 do not have any overlap and therefore A2 and A4 is another possible output subset. Any single individual activity, for example A5 itself or A1 itself or A3 itself, it cannot overlap with any other activity because there is only one activity in the subset, so that is also a possible answer. Similarly, A1, A3 and A5, these three activities here, they do not overlap with each other and therefore this is also a possible output. Recall that our goal is to come up with an output subset that has the maximum number of mutually compatible activities. So in this case, O1 and O2 have two activities, O3 has just one activity and O4 has three activities. Therefore, O4 is our optimal answer. Let us now try to come up with a greedy algorithm that always computes an optimal solution to this problem. Now because our goal is to select largest number of mutually compatible activities, what if we always select the smallest activity first? Would that work? Unfortunately, it turns out no. And it is very easy to come up with a counterexample. Here is one. In this example, A2 is the smallest activity. However, if we first select A2, we cannot select A1 or A3 because A2 overlaps with both. However, that is clearly not the optimal solution. Instead of A2, if we selected A1 and A3, we would end up with the larger subset of mutually compatible activities. So what else can we do? What if we always select the activity that overlaps with smallest number of other activities? Would that work? Maybe not. Here is a counterexample. In this example, activity 6 has overlap with only two other intervals, 5 and 7. All other intervals have overlap with at least 3 or 4 other intervals. So if we pick activity 6 over here, we cannot pick activity 5 and activity 7. Now from here onwards, no matter which intervals we pick, we can only pick two more. So let's say we pick 1 and 11. So we end up with a solution with 3 intervals. But clearly this is not the optimal solution. We could have instead simply picked interval 1, 5, 7 and 11, and that would have given us a mutually compatible subset of 4 activities, and therefore this is also not an optimal solution. So likewise, it is easy to come up with several greedy heuristics for solving this problem, and for most of them it is straightforward to come up with counter examples showing they won't work. So here is a correct greedy algorithm for the problem that always works. So first we sort the input set of activities in increasing order of their finish times. Then we pick the activity that ends first. After this, we eliminate all those activities that have an overlap with the chosen activity. And after this, we simply repeat the first two steps on all the remaining activities until there are no more activities left. So here is an example to illustrate the working of this algorithm. So of all these activities, activity 1 is the one that ends first. All other activities are ending after this point. So we select activity 1. Having done that, we need to throw away those activities that have an overlap with activity 1. So clearly activity 2 and activity 3, which overlap with 1, they cannot be in our solution. Now we simply repeat this on the remaining activities. So activity 4 is the one that ends next. All other activities are ending after this point. So we next choose activity 4, and we have to throw away the overlapping activities with 4. So activity 5 and activity 7 that overlap, they cannot be part of the solution. After this, activity 6 is the next that ends. So we choose activity 6, and if there are any other remaining activities that overlap with 6, they need to be thrown away, but there are no such activities right now. The only other remaining activity is activity 8, which has no overlap with the chosen activities. So this is our final answer. Activity 1, 4, 6 and 8 is the final answer. So why this algorithm works? A detailed proof of correctness is beyond the scope of this video, but here is an insight that will help you appreciate the algorithm. Any correct solution to the problem would look something like this. Essentially a series of activities that do not overlap. To this solution, if you add an activity that ends first, assuming it is not already part of the solution, one of two things would happen. In the first case, if the activity that ends first does not overlap with the first activity of your solution, adding it will improve your solution. Another possibility is the activity that ends first has an overlap with the first activity of your solution. So adding the interval that ends first, you will have to drop the first interval or first activity of your original solution. But note that the overall size of your solution remains the same. You dropped one interval and you added one interval. Therefore, adding the interval that ends first cannot make your solution any worse. It can only improve it. Also note that the activity that ends first cannot have an overlap with more than one activities in your original solution. Since it is the activity that ends first, it must end before or at the same time as the first activity of your original solution. Here is an iterative function for solving the activity selection problem. Capital S is the input set of all the activities A1 all the way up to AN. We assume that activities are sorted in increasing order of finish times. So A1 finishes before A2 and so forth up to AN. The total number of activities is N. Capital O is the output set, the desired output set of activities that are all mutually compatible. And J is the index of the latest activity that is added to capital O, the output set. The output set O is initially empty. So as the function begins execution, in the first line we can directly add activity A1, the first activity in set S, to set O, because recall that these activities in set S are sorted in increasing order of finish times. And then we set J equal to 1. So J is the index of the latest activity added to O. After this, in this for loop, we iterate through the remaining activities in S. In the first iteration of this for loop, J will point at A1 and I will point at A2. In each iteration of the for loop, we simply check whether the finish time of the jth activity is less than equal to the start time of the ith activity. If so, it means that the jth activity and the ith activities are compatible, there is no overlap, and therefore we can simply add the ith activity to output subset O and we can update J to I. However, if that is not the case, it means the two activities are not compatible and we simply move on to the next activity in the set S. At the end of this for loop, the subset O will have a maximum sized subset of mutually compatible activities from set O. So we simply return O. That is our desired answer. Thank you for watching. I hope this was helpful.